Okay, great. So for our next talk by Hanliang, Zhang, and collaborators about scalable, validated code translation of entire projects using large language models. So please get started.
Hello, everyone. I'm Hanliang Zhang, a PhD student from the University of Bristol. I'm very glad to present here our work, Scalable Validated Code Generation of entire projects using LLMs. This is a joint work with AWS, and my collaborators are Cristina and Meng from Bristol, Brendan and Daniel from AWS. The background of this research stems from the industrial need of translating security-critical code bases into Rust. Specifically at AWS, we encounter practical need to migrate several Go code bases. While there exist works that rely on symbolic techniques for automatic code translation, the code produced by such tool is often not idiomatic, and thus less maintainable. As a result, we proposed to develop an LLM-based tool for translating existing Go source code into Rust. However, real-world code bases are often of large code size and are organized into complex file hierarchy. While LLMs have shown their power of producing good quality of code, the limitation of context window blocks us from translating whole repositories all at once. To scale up, the general approach we follow in this work is to modularize the translation query. A repository is partitioned into individual translation units, like a function, a type, or a global variable. These code fragments are then translated by the LLM following the dependency graph, producing code fragments in Rust, which are later on combined into an entire project. However, being modular is not sufficient in itself. When applying the modular translation algorithm, two key challenges arise. Firstly, we discover that LLMs are often unreliable when translating features of the source language that do not have a direct mapping to the target language. For example, in this Go program, a global variable x is initialized by calling a function. Without specific instructions, the LLM can produce Rust code that largely simulates the syntax of the Go program, where the static variable is initialized by directly calling the function as well. However, this is invalid in Rust as static variable can only be initialized by constant expressions or constant functions. Therefore, this default translation could not compile. There are multiple ways to salvage this translation. For example, one could rely on the lazy construct from a standard library, which supports lazy initialization and therefore allow initialization by calling functions. Similarly, one could rely on third-party libraries that provide the same functionalities. And there are perhaps many other solutions. While the LLM can sometimes generate correct code fragments, it is not guaranteed that these fragments consistently use any of the solutions. To resolve issues like this, we propose a technique called feature mapping that incorporates predefined high-level translation rules with LLM's code generation. These rules specify how particular source language features should be mapped to constructs in the target language and allows for customization. This approach improves both the compilation success rate and the consistency of the generated code. Secondly, it is challenging to validate the translation in terms of semantic equivalence. Since we translate the program modularly, we aim to measure semantic equivalence at the function level. Here, we assume that the Go program comes with a suite of unit tests that achieve high functional coverage rate. While these unit tests can be used as specifications of the original functions, it is not obvious how we can transform these unit tests into the functional specification of the translated Rust functions. It is especially challenging when the function signature involves non-primitive types or user-defined types, as LLMs may generate code that contains types that are not compatible with the original source code, meaning that the runtime values witnessed by executing the unit test cannot inhabit the Rust types. In this work, we proposed a technique called type-compatibility check, which dynamically checks that a Go type and the Rust type can safely interoperate, allowing differential testing of the translated Rust functions. We incorporate the two proposed techniques into the modular translation workflow. Before starting the translation, we collect execution snapshots for every function in a source project. Execution snapshots are a pair of input-output examples that serve as specification of the function to be translated. For each partition code fragment, we construct feature mapping prompt that specifically instruct the LLM for target features, obtaining a candidate Rust code fragment. And this fragment is then statically checked against the corresponding feature mapping rule and dynamically checked for type compatibility by using the execution snapshots. If any of the checks failed, we recreate for a new translation. We set a finite budget on the number of regeneration to avoid infinite loop. We call this translation process a type-driven phase. After type-driven phase, we obtain a type-compatible project translation, and we apply an additional semantic-driven refinement phase. We run the oracle constructed for all functions. If any of the tests failed, we requery for a new translation with signature frozen. Again, we set a budget to prevent infinite loops. After all functions are refined, we combine all the code fragments to an entire project as the translation of the original project. Now I will go into details of our two techniques. The first technique, which we call feature mapping, comprises predefined high-level translation rules for prompting and checking LLM's code generation. For the code snippet containing the global variable initialization, as discussed before, we apply this particular rule. Note that for clarity, we summarize our predefined translation rules by using a slightly non-standard inference style rule. We first check the shape of the source code, which is a global variable initialized by a function. Then we construct a prompt to specifically instruct the LLM to use the lazy construct. While doing so, there's no guarantee that the LLM will actually generate the code we want, or even any code that makes any sense. We therefore apply static checks on the generated code to enforce the rule that the code is indeed a static variable initialized by the lazy construct. Note that we don't impose any additional constraints, and the LLMs are even free to generate names of the global variables. This is for idiomaticity purposes, as Go prefer camel cases, where Rust prefers snake cases. Now, if the check failed, we give out the current translation and requery for another one. Once obtaining code fragment that satisfy the desired pattern, we perform post-processing, which is not necessary for this simple case. So in summary, a feature mapping rule comprises three parts: a specific instruction in the prompt, the static checks that enforce the rules, and necessary post-processing steps to instrument the code. Of course, there are many other differences in features between Go and Rust, like error handling mechanism, where Go uses error return value, and Rust uses result enumeration. Also, there are huge gaps in programming abstractions where Go uses structural interface and Rust apply nominal traits. These challenges can also be handled by our feature mapping rules. We have rules that map a fallible Go function into a fallible Rust function by requesting and checking the usage of result enumeration and a specific error type called anyhow error, which is a third-party dynamic error type, allowing casting between dynamic error, simulating common coding patterns in Go. Note that these kind of rules allow for customization. The user can choose different error types to map into and modify the rules and prompts accordingly. Also, we have rules for systematically and modularly map an interface and its implementations to a Rust trait and implementations. Note that these rules require post-processing of the code generated by the LLM in order to preserve potential sub-interfacing relations. For detailed description of these rules, we refer to the paper. All these rules contribute to higher compilation success rate. Also, by applying these predefined translation rules, we have a very clear understanding of the code generated by the LLM, which facilitates manipulation of such code. For example, combining code fragments with other fragments, constructing oracles, etc. After obtaining candidate function translation, we need to consider constructing an equivalence checking oracle. We follow a differential testing approach. We first execute all existing unit tests for the Go project to be translated. For every function covered by the unit test, we collect execution snapshots, which are pairs of function input-output values. These input-output values are then ported into the Rust program by using serialization and deserialization, where we construct a test harness such that we execute the Rust function with input values from the execution snapshot and check whether the Rust output equals to the output values from the execution snapshots. Note that these steps requires that the input-output types from both sides need to be compatible or interoperable. Additionally, we model side effects such as global states, input states mutations, which are omitted in the above diagram. In our experiments, we noticed that sometimes LLMs generate translations with incompatible type, which lead to incompatible function signatures, causing the equivalence checking oracle to crash. For example, consider this Go function that takes a slice of string as inputs. The LLM can generate a plausible translation, which is a function that takes a vector of string as inputs. This translation is incorrect because upon checking execution snapshots, we found that the null value has ever been an input value to this function f. However, null value does not inhabit the Rust type vector of string. Recall that we differentially test a Rust function by porting Go values into Rust by deserialization. This process is doomed to crash at runtime. As a result, we devised the notion of type compatibility, which says that any feasible values that can inhabit a type in the original Go project should also be able to inhabit the corresponding type in translated Rust project. Type compatibility ensures the equivalence checking oracle can be constructed without runtime crashing and can filter out wrong translation early. During the translation, we enforce type compatibility check. For the previous translation, we look at the function signature and found that the input type is not compatible with the original input type, as it does not permit the null value. Thereby, it is rejected, and we proceed to recreate for a new translation. Now, the input type of this new translation is wrapped by an optional, and therefore null value inhabit this type, and so does any other values. This time, the function signature is type compatible, and we accept it and proceed to later phases of the translation. To evaluate the efficiency of our approach, we select 8 real-world code bases as benchmarks, with size ranging from 300 lines to approximately 10,000 lines of code. We target at popular code bases, and we believe that popularity reflects idiomaticity of the code base. Also, we select benchmarks that are with unit tests of high functional coverage rate. Our experimental evaluation shows that our approach achieves very high compilation rate for the benchmark selected. Measured by the percentage of function translated that successfully compiled, we achieve an average of 98% of success rate. Our approach also shows a relatively high input-output equivalence rate, similarly measured as the percentage of function translated that successfully passes our oracles. We achieve an average of 73% of success rate. Also, the translation consists of 100% of safe code. We also ran an evaluation study where we don't apply the feature mapping techniques, and the success rate drops drastically. Without feature mapping, LLM may produce code fragment that fails to compile, or fragment that is in conflict with other fragments, causing the translation loop to halt quickly. We also ran an ablation study where type compatibility checking technique is removed. We noticed a drop in the success rate due to translation that have incompatible types. So as a conclusion, in this work, we developed a scalable go-to-Rust translator that can produce validated code. We propose 2 techniques. feature mapping, and type compatibility that can improve the quality of the translations. And you can find out public artifact at this URL. And a public GitHub repository is coming out soon as well. And that's so much for my talk. Thanks so much for listening, and any questions are welcome.
Thank you. So yes, we have a question. Yeah, in blue. Is there? Yep. You give them the mic over there, please.
Hi, Milin Chabi from Uber. Interesting work. Can you speak about how you are handling concurrency and transforming Go code to Rust code, both shared memory and message passing?
Thanks. That's a good question. We don't handle concurrency at this moment because that's a really hot feature. We believe that if there is a chance of defining like high-level translation rules saying like current like specific concurrency primitives can be translated into like corresponding Rust primitives or a combination of Rust primitives, then we might be able to do the translation. But for now, we don't consider concurrency.
Another question: how about how are you handling library calls?
That's a great question. So the benchmark we selected only relies on standard libraries or libraries of well-known well-known third-party libraries. And typically, LLMs have the knowledge of selecting the corresponding library APIs, and we have an ongoing work that kind of extend the current framework to handle like arbitrary third-party library by using some RAGing techniques. So yeah.
Thank you.
Good. Another question over here, please, the front.
Hi, I wonder how you check the equivalence of the two codes. Why the Rust code is considered as the correct translation of the original Go code.
Yeah. Thanks for the question. As discussed in the previous slides, we kind of construct oracles by using existing unit tests from the Go repository. So basically what we do is that we execute all unit tests from the Go repository, and we collect execution snapshots, which are kind of like input-output examples for every function in the Go, for the Go functions. And by using some introversion techniques, we kind of ported this input-output example into Rust and used that as the specification for the function translated.
Okay, we have time for a question. You have a question? Okay, yeah, let's ask a question from here.
Thank you for the talk. How do you handle borrow checker? How frequently did it happen that the borrow checker rejected the translated program?
Okay, thanks for the question. So we don't particularly handle borrow checker. We kind of rely on the LLM to generate correct code. But as you said, the borrow checker of Rust is very strict. It sometimes produce compilation errors, and we do encounter some hard cases where the original Go code is written in a really, I would say, not Rusty pattern, like you use share mutability, share ownership, and all that stuff, and such function cannot be translated. So yeah.
How frequently did it happen?
In our benchmark, it happens not so frequently. Like most of the code are translated just fine. So.
Okay, we have time for one more question. Maybe right here in the second row. And in the meantime, if the second speaker can get ready.
Okay, so I want to argue that relying on the unit test as the ground truth is both expensive and so limited. So any idea on how to fix it?
Yeah, thanks for the question. So we have tried fuzzing as well. So basically we can construct fuzzing tests on the Rust side. But the problem is that the input example generated by the fuzzer is of less quality than the example coming from the unit test. And we've also have some previous work try formal methods and by using model checker and all that stuff. But the question is that they don't scale up to the level of, say, 10,000 lines of code. So currently, we found a unit test being our best option, but we're also exploring by using, say, like better fuzzer or stuff like that. Yeah, thanks.
Okay, let's thank our speaker one last time. Yeah.